Welcome back to the Deep Dive. Today we're tackling one of Python's most, I think, elegant features, but one that's also often misunderstood.
Oh, absolutely.
Think about those moments when you've built this incredibly useful custom class. Maybe it's a complex financial instrument or some kind of specialized unit of measurement.
And you've poured hours into it. It holds all the right data. It calculates everything perfectly. But then you try to use the simplest thing in Python, the humble plus sign.
Right.
And your powerful, beautiful object just throws up its hands and gives you a type error.
And that's the moment, right? That's when you realize your sophisticated code breaks the most basic flow of the language. Instead of writing something clean and beautiful like vector A plus vector B,
You're stuck writing something clunky like
Yeah.
a dot add vector b.
it's hard to read. It doesn't feel like Python.
It really breaks that core promise of intuitive, readable code. But what if you could teach that plus sign exactly what it means to add two of your custom objects?
And that is the essence of our deep dive today, Python operator overloading. So our mission is to unpack these specific double underlined special methods, the dunder methods as they're called,
Right.
the ones that allow standard Python operators like plus or divide or even in and functions like len
Yeah.
to just work, to function seamlessly on objects that you created.
We want to show you not just what they are, but really how they work together to create that truly idiomatic Python code.
Because once you grasp this, it just unlocks a whole new layer of expressiveness in your code.
It really does. You move from writing code that's just functional to writing code that reads like a language designed for that specific problem.
Okay, let's unpack this.
Let's do it.
So at its core, operator overloading. It's kind of like Python's way of defining a contract, right?
Exactly. It allows operators like plus, minus, multiply to be flexible. They don't just have one fixed meaning for, say, integers.
It can be overloaded.
They can be overloaded to mean whatever you need them to mean inside your class. And the benefit, really, is writability.
It makes sense. When you overload, you stop forcing people, and that might be you in 6 months, to remember all these verbose method names.
Yes. You're making your custom classes work more like the fundamental types because they respond to those fundamental symbols.
The classic example our source material brings up is geometric, adding 2 points in 2D coordinates.
Right.
If I have point A and point B, the human readable math is simply A plus B. Why should the code be any different?
It shouldn't be. And the mechanism that lets us do this is the use of those special methods,
The dunder methods?
the dunder methods. You can think of them like add or len as a sort of switchboard operator.
Okay.
When Python sees an operator used on your object, it doesn't guess what to do. It calls that switchboard and asks, hey, does this object have a method named specifically to handle this operation?
So if I wrote A plus B, Python looks at object A and says, does this thing have an add method? If it does, great, it runs my custom logic.
And if it doesn't?
Then you get the type error.
Exactly. It's a very structured lookup process. And while we're going to cover the most critical ones today, if you ever need the complete list, the Python data model reference documentation is the place to go.
That's the ultimate guide.
It is.
But what's really fascinating here is that we often think of this just for math symbols, but the system applies to so many, well, non-mathematical actions too.
That's a great point.
Hmm.
Let's look at the methods that handle interaction with built-in Python functions, because these are absolutely essential for making a class feel native.
The most common one has to be len. If I have a custom object that represents, I don't know, a curated collection of data.
You want to use len on it.
Of course. Want to see how many items it contains, just like a list.
And if you don't define how, Python won't know. When you call len on your class, Python is specifically looking for one method .self.
And if your class defines that, and this is a key detail, it returns a non-negative integer.
Then the len function just works. It's a clean, simple interface.
The same idea is behind iteration, right? Which is so central to Python. If I build a custom playlist class, I have to be able to use a for loop on it.
For sure. To make your object iterable, the for statement calls the built-in iter function, and that function in turn calls iter self.
So defining that method is basically the gateway to using your object in loops, in list comprehensions.
All of it. It turns your class from just a static data holder into something dynamic that Python can actually walk through.
And what about one of the most useful operators for any kind of container, the in operator?
Yeah.
How does Python figure out if something is in my custom object?
That capability relies entirely on the special method contains self item. If you implement that, you get to define the complex logic for what it means for an item to be inside your object.
So I can write that really clear declarative code if apple in my basket.
Exactly.
I think the biggest practical win for day-to-day development and debugging, though, is how an object presents itself when you print it.
Oh, the dreaded memory address.
Yes. I remember when I first started, I'd print my classes and get something totally useless, like main. My object to object adds 0x something.
It tells you absolutely nothing, and that happens because you haven't defined the two most critical output methods, str and repr.
Okay, let's really focus on the difference here because I think this is where a lot of learners get tripped up.
It is a crucial detail. So when you use str object or print or format an object for an end user, Python calls str, self. This method is designed to return a human-readable representation. Think of it as the output you'd want a user to see in a log file or on a screen.
So for my geometric point object, str might return something like point at x10, y20.
Exactly. Now contrast that with repr self. This is the unambiguous developer-facing representation.
Okay, so this is for me, the programmer.
It's for you. It's what Python uses for debugging, and it's what you see when you just type the object's name into the interactive console. A good repr output should ideally be a string that, well, if you pasted it back into the interpreter, it could recreate the object.
So for my point, the repr would look more like point 10, 20.
That is the gold standard, because then you can just copy-paste and you have the object back.
I see.
A common mistake is just forgetting repr. If str isn't defined, Python will fall back and use repr. But if neither is defined,
You get the useless memory info.
you get the memory address. Always define both for truly robust, debuggable code.
That is a deep dive nugget right there.
Okay.
Before we jump to all the math, let's briefly mention the other end of the object lifecycle, cleanup.
Right. The destructor method,
Okay.
del self. This is called right when an instance is about to be destroyed or garbage collected.
And while Python handles memory pretty well on its own.
It does, but this method is your final chance to do any necessary cleanup. Closing open file handles, disconnecting from a network socket, releasing any non-Python resources. It just guarantees good hygiene.
Makes sense. So we've covered basic functionality.
Yeah.
But for any custom object to be truly useful in, complex logic, it has to interact with other data.
Yes.
And that means defining how it relates to other objects. You have to tell Python, is my object greater than, equal to, or less than another one?
This is non-negotiable for any real-world code. Imagine a class representing a financial portfolio. How do you sort them? How do you know if portfolio A is better than portfolio B?
You can't just assume Python knows.
You have to bake those rules in.
Okay, let's start with the cornerstone, equality. How do we tell Python that two of our complex objects are, for all intents and purposes, equivalent?
The equality check x equal y is handled entirely by the eq self-other method, and this method is crucial. It has to take self and other and return a Boolean.
And I get to define the criteria for that.
You decide the rule. Is it equality of all attributes, just one key attribute? It's up to you.
What if I try to compare two objects of totally different types, like my custom point object and just a regular Python list? What happens inside EQ?
That's where good practice comes in. Inside E, you should first check the type of other. If they're incompatible, your method should return not implemented.
Not implemented, not false.
Never false. Not implemented is a signal to Python. It says, I don't know how to compare these two types. This allows the interpreter to then try the check on the other object, other.eq self.
Oh, that's a really fundamental distinction.
Yeah.
Okay, so once we have equality, we need the whole suite of relational operators for sorting and filtering.
Exactly. And there's a set of methods for all of them, and they all follow that same self-other pattern.
Let's run through them.
For less than, the less than symbol, you define elt. For greater than, you use gide. The not equal to operator uses ne.
And the inclusive ones.
Right. Greater or equal to is b, and less or equal to is le.
Wow, that seems like a lot of methods just to handle 4 basic comparison symbols.
It is.
I mean, if I define elt and e, couldn't Python figure out the rest, like det or net?
It is a lot of boilerplate code, and you've hit on a major practical issue. Fortunately, this is where Python gives us an optimization.
Okay.
If you define at least eq and one of the ordering methods, let's say ae for less than, you can use the built-in functools.totalOrdering decorator.
Oh, now this is where it gets really interesting. Tell us about that decorator.
The total ordering decorator essentially fills in the blanks for you.
Hmm.
If you tell it how to handle and ate, it automatically figures out the logic for greater than, less than, or equal to, and so on.
By just combining those two fundamental operations.
Exactly. It saves you from writing 5 basically redundant methods. It dramatically reduces your code and the potential for bugs. It's a must-have for any class that needs to be sorted.
Okay, this is the big payoff. We started with the pain point of the plus sign not working. This is where custom objects truly start to behave like native numbers.
This is the aha moment. Whether you're building a matrix class, a physics simulation, anything, you just want A plus B to work.
So let's run through the core arithmetic methods first.
They're all structured similarly, taking self and other. For standard addition, the plus sign, the method is add.
Add.
For subtraction, you implement sub. Multiplication is mul.
And division.
Specifically true division, the slash, is truedaf. And then for the remainder, modulus, that's mod. And finally, exponentiation, the double asterisk, uses pow.
That seems like a pretty straightforward mapping. But here's a common point of confusion. What happens if I try to add my custom object to, say, a normal integer? If I write my vector plus 5, it works. But what if I reverse the order and try 5 plus my vector?
That is the most important distinction in numeric overloading. When you write my vector plus 5, Python calls myvector.add5. Simple enough.
Right.
But when you write 5 plus my vector, Python can't just force that native integer 5 to have an add method that understands your vector object.
So it just throw an error.
It tries one last thing, and this is where the reflected operators come in. If the left operand, the integer 5, fails its add check, Python tries to call the right operand's reflected method.
So it calls myvector.rad5.
Exactly. The R stands for reflected or reversed.
So we basically have to define both the normal operation, add, and the reversed operation, rad, if we want our object to play nicely with native types on either side of the operator.
If you want true compatibility, yes. And in many cases, if your addition is commutative, if A plus B is the same as B plus A, your rad method can just call your add method.
And the not implementer rule still applies here.
Critically, if your method sees a type it can't handle, it must return not implemented. So Python knows to try the other side instead of just failing.
That's a deep insight. Now, what about assignment operators? We use plus or all the time to modify something in place. Does add handle that?
No, it doesn't. And this brings up our third category, in-place operators. When you use A plus B, a new object is usually created and assigned back to A.
Okay.
But when you use A plus as B, Python looks for a different method. IAdd, the I stands for in place.
So if I define IAdd for, say, a custom list-like class,
Right.
I can modify the list directly without creating a massive new copy in memory. That's way more efficient.
Precisely. If you're dealing with large mutable data structures, defining IAdd or ESUB and so on is key for efficiency. And that method usually needs to return self after it's done its modification.
Got it. Okay, finally, let's just quickly cover the methods for bitwise and logical operations. These are more specialized, but necessary for low-level stuff.
They follow the exact same convention. For bitwise operations, XOR is XOR, OR is OR, and AND is implemented in AND.
And defining those gives you pretty much comprehensive control over every standard Python operator.
It really does. It ensures your custom object can function in almost any context a built-in type can.
What a journey. I mean, we've gone from simple addition all the way to reflected and in-place operators. Let's pull back and summarize the key takeaways.
I think the primary takeaway is that Python's elegance relies on these contracts. Operator overloading uses these special methods like add, len, reper2, map familiar symbols onto your custom class behavior.
Which achieves that intuitive code and makes your custom objects feel, well, seamless with the rest of the language.
And the value here isn't just academic, it's so practical. You can build incredibly readable, efficient, and importantly, debuggable code.
You define all the complexity behind the scenes.
Right. You handle the mixed types with rad and not implemented, but the person using your class just sees simplicity. Complex things like calculating the difference between two time periods just looks as clean as time A, time B.
That really is the mark of an experienced Python developer. Okay, now for one final provocative thought for you to mull over. We talked about adding 2D coordinates, pretty straightforward, but let's push that idea into abstraction. Imagine you have a custom class representing a set of user permissions,
Okay.
and you define addition, add, to logically combine two sets of permissions. Maybe it gives the user the superset of both.
So it's basically a logical OR operation, but hidden behind the plus sign.
Exactly. So what happens if you then overload multiplication, mul, For that same permissions class, how could you define multiplication to create a meaningful result?
Oh, that's interesting.
Could it represent the intersection of permissions, the minimum shared access? Could it represent, I don't know, compounding or elevating permissions in some way?
Thinking about how to map abstract non-numeric concepts onto these basic arithmetic symbols, that's the true test of mastering this.
It forces you to define the mathematical metaphor for your own data
I
structures.
love that.
Food for thought for your next big project. Until next time, keep that code clean.